Hey everyone, welcome back. In today's video we're doing trig integrals. So basically in this video we're going to be doing some integration of more complex problems, and particularly when it comes to trigonometry. So before we get started, let me just put down a reference for you all. Remember that this is the trig identities, right? Or Pythagorean identities. And when it comes to trig integrals, these are very helpful, so you want to always make sure to reference this. One way to remember this is all you got to do is remember the first line. So sine squared x plus cosine squared x equals to 1. And from the first one to the second formula, all we got to do is divide everything by cosine squared x, right? So if you noticed, if I divide sine squared x by cosine squared x, I get 10x. If I divide cosine squared x by cosine squared x, you get 1. And 1 over cosine squared x is secant squared x. So this is one way you can do to memorize this, right? So now let's try to actually do the problems. So for the first one, there's nothing too difficult about this one. All you gotta do is use substitution. So in this scenario, I could actually let u equals to cosine theta or sine theta, it doesn't matter. But in this scenario, you know what? I don't want to deal with negatives, so let's use sine theta for my u. So I'm basically substituting sine theta as u. So to derive that, that's basically cosine theta, d's theta. I want to isolate these theta. So it's 1 over cosine theta du. And if you notice already, this is very easy for us to cancel out. So we let sine as u. And right now we want du. So I replace all this to d theta. So that's 1 over cosine theta du. And notice I can beautifully cancel out the cosine theta, so I'm left with u du, which is very simple to integrate. That's u squared divided by 2 plus c. So when we're here, always make sure to plug back in the u, which is sine in this scenario. So there you have it, that is our answer. So nothing too hard for this problem. This kind of ties in with my previous video on u substitution. If you haven't watched that, I do recommend it because u sub is a huge thing when it comes to integrals. So now let's move on to the second one. This time we have something slightly harder. We have secant theta times tan cubed theta. So when it comes to these problems, the first thing we want to do is think about how we can kind of break it down before actually integrating it. So in this scenario, I can't directly use u substitution because let's say I do u as tan theta, for example, like it wouldn't work because our final value, if we derive that, it's gonna not be able to cancel out everything, so we can't directly use u sub. So what we want to do is refer back to my Pythagorean identity. So to break it down, notice that I have tan squared x here, and I have a tan cube here. So maybe I could do that. Maybe I should break it down. So I'll leave secant theta as it is, and tan cube theta is basically tan theta times tan theta times tan theta. In this scenario, I see that there's a tan squared, so maybe I could do that. So I'm basically rearranging my integral to look like this. This is the same as this. And then now we can try to use our Pythagorean identity. So we know that tan squared theta plus 1 equals to secant squared theta. So right now we have a tan squared theta here. So what I want to do is isolate that. So to get tan squared theta alone, that's secant squared theta minus 1. So I can plug that in right here. And we get secant theta times tan theta multiplied by tan squared theta, which is secant, better to put brackets, secant theta minus 1 d theta. So now I know when you look at this, it's like, oh my gosh, from here to here, we kind of made it complicated, but no, if you think about it, now we can use U substitution. So what U substitution do we use? Well, in this scenario, we can use U substitution, and I can say I want it to make it to secant theta. Now, when it comes to U substitution, in the beginning, it can be confusing as to what you want to put as U, but slowly, as you practice more, you'll know what to use. And even if you do use wrongly, you can always change it and use another one, right? So when it comes to substituting your numbers, don't be afraid to try different values for your U substitution. Sometimes it might not work out, but then all you gotta do is try again, right? Anyway, so in this scenario, I let U equals to secant theta. If I derive that, remember that's basically secant theta times tan theta d theta, right? And I want to isolate that, so that's just going to be 1 over secant theta tan theta du. So now I want to plug in secant theta in. So now, if I plug in secant theta, I see there's a secant theta here and a secant theta here, but notice when I finish deriving, I get 1 over secant theta times tan theta, right? And you notice that we have a secant theta and tan theta here. So we can beautifully cancel out. So in this scenario, we want to leave the secant theta as it is. So we have secant theta times tan theta. But I do want to make this secant squared theta as my u. So I have u squared minus 1 d theta, which is 1 over secant theta times tan theta du. And as a result of leaving the secant theta in the beginning as it is, we can beautifully cancel it out. And we're left with u squared minus 1 du, which is very beautiful because we beautifully cancel it out. So now we're left with that. And now all you gotta do is just integrate it. So u squared minus 1, that's u cubed, and that's 1 over 3. And then the minus 1 becomes minus u, and then plus c. And then our last step is to plug in, plug in back the u. Remember our u was secant theta, so secant cubed theta minus secant theta plus c. And there you have it, that is our answer. So notice here, there isn't like a strict formula to how to do these, but you want to make use of the Pythagorean identity. So yeah, that's it for the second question. Now let's move on to our third question. Now, in this scenario, we don't see any trig stuff. So why is this even in our video, right? So when we look at this problem, we see that it's very complicated. The denominator is a polynomial function. So what do? How can we make, how do we do this problem? Let's say if I make u equals to x squared plus 2x plus 2, that wouldn't work because if I derive it, I get 2x plus 2, and I can't cancel anything. It's not like our numerator is 2x plus 2. No, we can't cancel it, so we can't directly use u sub. So what do? In these problems, when we have a denominator that looks something like this, and obviously my video is called trig identity, so there's definitely some trig stuff in it. So what do? So in this problem, what I want to do is try to complete the square. Remember how to complete the square. So We want to complete the square for the bottom one, and I'll explain why we're doing that later on. But basically, recall when you complete this square, basically it looks like, you know, in algebra you probably learned there's different types of quadratic functions, right? And when you complete the square, it's when it shows the vertex, basically. So in this scenario, remember when we complete this square, we want to basically isolate the number outside. And remember the formula b over 2 squared when it comes to completing the square. So we got to identify what b is. In this scenario, b is 2. So 2 over 2 squared is just 1 squared, which is just 1. So when we get this value, what we want to do is add it in to our equation. So we plus 1 here. And because we plus 1, we got to also subtract it so that it's equal. Okay? And in this function here, you can see if we factor that out, we get a beautiful function x plus 1 squared plus 2 minus 1, which is 1. So this is our form, our new form. So that's how you complete the square. And now, putting it back in, we have x plus 1 squared plus 1 dx. So when it comes to this now that we have this, you'll see why we completed the square. Notice that this is very similar to the integral, right, of x squared plus 1. Recall that the integral of 1 over x squared plus 1 is basically tan inverse of x, remember? Plus c. You can also think of it this way. If I have y equals to tan inverse, the derivative of that is equal to 1 over x squared plus 1, remember? So we can see that this has a very similar form to this. So now we can use our u sub. So our u can be u equals to x plus 1, right? We want this to look like this. So du is just equal to 1 dx. So now that we have that, we can plug in the u, which is that. And then we don't have anything to cancel out. Du is just equal to dx. So that's it. And then now all we gotta do is integrate it. And we already actually integrated it, right? It's basically tan inverse. So our final answer is going to be tan inverse of u plus c, which is equal to tan inverse of x plus 1 plus c. So there you have it. This is how you approach these problems for trig integrals. I hope you enjoyed this video, and I'll see you guys again next time. Thank you.